Okay, I'm gonna try to be very short today, hopefully, but let's see. Okay, so last time we talked about the proposition that we showed was that so far what we know about simplex is that if you start with a feasible dictionary and you apply pivoting operation, you end up with a feasible dictionary. That's number one. Number two, under pivoting operation, the value of the objective function remains non-decreasing, meaning that if you have a dictionary and you apply the pivoting operation, in the next dictionary the value of z cannot decrease. Okay, that's what we said. And then we said that okay, what if you have a dictionary D? What if you have a dictionary D, and then you apply the pivoting operation to obtain the new dictionary D prime? Then under what condition? Well, I should say, if the value of the objective function remains the same, what can you say about the dictionaries, right? So you obtain D prime from D. If the objective value remains the same, then what can you say about the dictionary D? Well, what we can say is that the dictionary D is a degenerate dictionary, meaning that one of the basic variables in the dictionary D has value 0, right? That's what we meant by degenerate dictionary. Alright, so today what I want to talk about is that the termination of simplex. That is, are we guaranteed that the simplex will terminate? Right? How do we know that simplex will terminate? That's the question here. Well, in order to answer that, let's think about what happens if simplex does not terminate. Okay, so if the simplex does not terminate, again, so what is the meaning of simplex? Is this moving from one dictionary to the next by using pivoting? That's simplex. So if simplex is not terminating, then what can we say? Well, there are two possibilities, right? One is possibility 1, and in this possibility we keep getting a new dictionary. Okay, we keep getting a new dictionary as soon after applying the pivoting operation, you always get a new dictionary. So you have infinitely many dictionaries that can happen if it is not terminated. Is it actually possible? What I'm saying is that if the simplex does not terminate, one possibility is that as you apply the pivoting operations, you keep getting a new dictionary. My question is that possible? We keep getting a new dictionary after each pivoting. Is it possible? I see someone says no. Why? Why do you think we're going to get the same thing? I mean, why can't this be happening? Remember, I forgot to say, somebody actually answered the question that how many dictionaries are there? There are only finitely many dictionaries. And we're going to talk about that today. So I'm not going to say a whole lot of it. I think David knows the number of dictionaries from what he sent me in the email. So this is not possible. You cannot get. This is not a possibility because there are only finitely many dictionaries, and we will see why. So this is not a possibility. Now let's actually think about how many dictionaries are there. What is a dictionary? In a dictionary, basically, we choose. We have, remember, how many variables do we have, and how many basic variables do we have? Let me look into, yeah, so let's see if I can, no, not that one. Let me go back to the original, so this is a dictionary, right? My question to you is that in the general case, when I have a linear programming problem with n decision variables and m constraints, right? M for monkey and N for Nancy. I have m constraints and n decision variables. Then what is the number of basic variables? The number of basic variables is going to be the number of constraints, functional constraints, which is m, and the number of non-basic variables will then be the remaining ones, right? So each dictionary depends on the choice of the basis, right? Once you choose a basis, the dictionary is determined, right, by that basis. Am I making sense? So the question is, how many different ways, how many different possible bases are there? Okay, for each basis, I have a dictionary. So the question is, how many choices are there for a dictionary? Am I making sense? How many choices are there for a dictionary? And so here, let me ask that question here. This is the number of dictionaries. Number of dictionaries is equal to the number of ways of, let me suggest the number of possible bases. Okay, number of possible bases. Okay, how many bases are possible? Well, how many variables do I have? What's the total number of variables? The total number of variables, so this should be the total number of variables. From there I have to choose how many basic variables. What's the total number of variables? Plus functional constraints. So this would be m plus n, right? I have m constraints and decision variables. So the total number of variables, including the slack variables, would be m plus n. And from that, how many variables do I choose for the basic? For the base? For the basis. How many basic variables do I choose? Number of basic variables. So this would be total number of variables, choose the number of basic variables. And how many basic variables do I choose? M of them, right? You agree? So there are m plus n choose m dictionaries, possible dictionaries for a LP problem with n decision variables and m functional constraints in the standard form. Okay, so we know the total number of the total number of possible dictionaries. That doesn't mean the simplex goes over all the dictionaries. All I'm saying, this is the total number of possible dictionaries. Is everybody clear? So we know that there are finitely many. So this cannot happen that you keep getting a new dictionary after each pivoting operation. Okay. So what's the other possibility? One of you told me already that the other possibility is that you get to a dictionary di, and then you get into a cycle. So from di you get di plus 1, di plus 2, di plus k, But after di plus k, you go back to di. That is, when you apply the pivoting operation to di plus k, you get the dictionary di again. So that's a cycle. I'm calling that a cycle, that you apply the pivoting operation, you get to di, and then you get di plus 1, and as soon as you get to di plus k, what happens is that when you apply the pivoting operation to di plus k, you go back to di, and that's a cycle. It means that the simplex is now within a cycle, right? It's moving around, it's going around the cycle, and it's going to go there. Once the program goes into that, it's going to keep doing that, right, until the user realizes something is happening, and he has to what? What do you do when your program just runs and runs and runs? Well, you just terminate it, right? Manually you terminate the program, right? Otherwise it's going to keep running. Okay? So the question, this is called the cycling. This is known as the cycling phenomenon for simplex. Again, the question is, can cycling really happen? And the bad news is, yes, it can happen. Okay? But the news is not entirely bad. And we're going to see that in a second. The thing that I want to I want to say though, when cycling happens, something interesting happens though. What can you say? So when cycling happens, I claim that each of the dictionaries in the cycle is a degenerate dictionary. Okay? And can someone justify that? Each dictionary in the cycle is a degenerate dictionary. Can someone give me a justification of that? I am going to make some notation here. I'm going to say Zi is the value of the objective function obtained from dictionary di. Zi plus 1 is the value of the objective function corresponding to the dictionary di plus 1, and Zi plus k, that's the value of the objective function corresponding to the dictionary di plus k. Is everybody clear? What am I claiming? I'm claiming that all the dictionaries in the cycle are degenerate. What does it mean? One of the basic, in each case, one basic variable is 0. But how can I show that's the case? Remember what we said, going from one dictionary to the next, if the value of Z does not change, if the value of Z does not increase strictly, if the value of Z remains the same from one dictionary to the next, then the beginning dictionary has to be what? Degenerate, right? If going from di to di plus 1, if the value of the objective function does not change, then the current dictionary di has to be degenerate, right? So use that and tell me why all the dictionaries are degenerate. Why are all dictionaries degenerate? Yes, David, you want to say something?
I think you start with degenerate dictionary.
Yeah.
The value is going to change. So if you're stuck in the cycle, you're just going to stay at the same value.
Yeah, so basically, remember, we proved that if I start with the dictionary di and go to the next one, one thing I know for sure, that the value of the objective function is increasing, right? I should say non-decreasing. So the value of the objective function is non-decreasing, tells me that Zi is less than or equal to Zi plus 1, right? I know that. So I know that Zi plus 1 is less than Zi plus 2. I know that Zi plus k is larger than that, because The value of the objective function is non-decreasing under pivoting operations, right? But what do we know after di plus k? What's the next dictionary? What's the next dictionary after di plus k? di. So that means this is less than zi again, right? Well, zi is less than blah 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 and then less than zi, right? So what does it tell you? All these inequalities must be what? Equalities, right? If I say 1 is less than x is less than 1, it means x has to be 1, right? So because of these inequalities, then I know this implies that zi and zi plus 1, they are all equal. And what do we know? It means that going from di to di plus 1, the objective value doesn't change, which means di is a what? This implies di plus 1 di plus k are degenerate dictionaries. Why? Because how do I know di is a degenerate? Because going from di to di plus 1, objective value did not change. And last time we proved that when the objective value doesn't change, going from one dictionary to the next, the current dictionary has to be degenerate. Okay, and so on. Again, degenerate means one of the basic variables in that dictionary is equal to 0. Is everybody okay? So that's my proposition, that each dictionary in the cycle must be degenerate. I guess I wrote it twice in any case. So cycling can happen though. Cycling can happen, that's the bad news. Cycling can happen, that's the bad news. But the good news is though, cycling is rare in practice. In fact, it hasn't been what should I say? It hasn't been detected in practice. However, there are theoretical constructions of problems, linear programming problems, where we do see that cycling happens. Am I making sense? So people have came up with examples of linear programs where cycling happens, but they didn't came out of application problems. That's what I'm saying. So in practice, in application, we haven't seen cycling, but there are mostly theoretical constructions of problems where we do have cycling phenomenon happening, which is concerning, but it is also sort of comforting that cycling is rare in some sense. Okay. Question is, can you avoid cycling by doing something? Can cycling be avoided? And the answer is yes, cycling can be avoided. How you can avoid it? Well, it turns out that cycling can depends on how you choose your entering and leaving variable. So it depends on the choice of entering, leaving variables, and it turns out that if you use Bland's rule, you can avoid cycling. Okay, but there are other problems with Bland's rule. We're going to see in a second. Okay, so even Bland's rule is anti-cycling. Okay, so if you use Bland's rule, you can avoid cycling. However, there are other problems with it, which is why we may not want to use it. So another phenomenon that can happen is called stalling. Stalling is not cycling. What is stalling? Stalling means that for a long time, for a long sequence of pivoting operations, the value of the objective function remains the same. Am I making sense? For a long time, so let's say for 200 consecutive or 1,000 consecutive pivoting operations, the objective function remains the same. However, it's not a cycle. After the 1,000th operation, it goes out of that stalling. Okay? The value of the objective function increases. So it's not cycling. However, the bad thing is that when stalling happens, is that for a long period of time, for a long number of iterations of the program, or for a long number of pivoting operations, the value of the objective function remains the same. And that could be problematic because it means that you're not being efficient. It's taking a long time to get to the final dictionary, okay? So in other words, here's a sort of a graph here. On the y-axis, I have the value of the objective function, and on the x-axis, I have the number of pivoting operations. So what can happen is that, okay, the value of the objective function increases at the beginning, and then for a long sequence of pivoting operations, the value of z stays the same. It may increase again, but then it may remain the same again for a long time. So that's what I mean by stalling. Here we don't have good news. Here stalling could happen a lot. Okay, stalling could happen a lot. Stalling could happen a lot with highly degenerate problems. There are problems by the construction of by the very nature of the linear program. It is highly degenerate, and because it is highly degenerate, we're going to see next week or when we come back geometrically what's the meaning of degenerate dictionaries. Okay, and for highly degenerate problems, stalling can happen a lot. Okay. And in fact, remember we said Bland's rule is anti-cycling, so you can use it to avoid cycling. However, the problem is, in 1974 or around that time, Evis Chatal said in a paper that even though Bland's rule avoids cycling, but Bland's rule actually makes stalling worse than the other methods of choosing, entering, and leaving variable. So stalling is made worse by Bland's rule. Okay, and it is so it performs worse than the other rules on small randomly generated problems. Okay. So what is good about Bland's rule? Well, it is anti-cycling. What is bad about Bland's rule? Well, stalling is made worse by this rule. Okay. So what should we do? We want to avoid cycling, but on the other hand, we don't want to get into stalling problem, right? Good thing is, should we worry about cycling? Remember I said cycling is rare. So because cycling is rare, maybe we should not worry about cycling. Maybe we should focus on stalling and avoid stalling rather than trying to avoid cycling. If it happens that cycling occurs, the program is taking a long time, then we should just depend on the user to manually stop the program, right? Does that make sense? So maybe we should focus on stalling problem. And so what should we do? Well, one thing we could do is that in the program we can. How many of you have taken a programming class? So in the program you can put in a counting function. So what the program is going to do is that it's going to count the number of consecutive pivot operations for which. Number of consecutive dictionaries for which the z-value have been the same. So you can put in a counting function that's going to count the number of dictionaries, consecutive dictionaries for which the z-value remained the same. And you can use that and say, well, if that counting function at some point is at least 250 or 500, you can say that okay, at that moment I'm going to start using Bland's rule. No, not sorry. What am I saying? Yes, I'm going to use Bland's rule to come out. Sorry, that's right. I'm going to use the Bland's rule in order to come out of that stalling. But as soon as I come out of the stalling, then I'm going to reset the counting function to 0 and start counting again the number of consecutive dictionaries, giving me the same z value. So you can use Bland's rule, but in a very careful way. Am I making sense? You want to use it just to get out of that problem, but you don't want to use it too much. Is that okay? But the idea is that we are not going to use. We're not going to worry about cycling. We're going to worry more about stalling. Is everybody okay? What's the complexity of simplex? You guys, when we took a programming class, did you guys talk about complexity of a algorithm or programs? Okay, complexity means basically how much time does it take for the program to complete. But I'm going to think about the time. So when I talk about complexity, I am thinking about the number of pivoting operations. The number of pivoting operations needed to get to the final dictionary as a function of the size of the problem. So what do I mean by the size of the problem? The size of the problem, you can think of it as the number of decision variables. Am I making sense? The size of the problem means the number of decision variables. So complexity means how many pivoting operations is required as a function of the number of decision variables, right? That's what I mean by the complexity. The number of pivoting operations required to get to the final dictionary as a function of the size of the problem. And the worst case complexity of simplex, well, the worst case complexity of simplex is exponential. That's the bad news. Bad news is that the worst case complexity is exponential, and when you took programming class, I'm pretty sure your instructor might have said, if you have a complexity of exponential, that's bad. On the other hand, though, the good news is, on average, in practice, simplex. Okay, what do I mean by the worst case complexity? Worst case means that the simplex moves through all possible dictionaries. Remember, you don't have to go through. Simplex usually will not go over all the possible dictionaries to get to the final. Okay. However, the worst case is it might go through all the dictionaries, right? So in that case, there are some problems where you get into exponential complexity, and we're going to see an example in a bit. And again, remember we talked about this. The number of dictionaries is what? The number of dictionaries was m plus n choose m, where n is the number of decision variables, m is the number of functional constraints. Now, if you have that m and n are the same, I'm just picking a case, then this is about 2n choose n, right? 2n choose n, and this is really 2 to the n. Okay? And so the total number of dictionaries is really a big number. The total number of dictionaries could be a big number, right? 2 to the think about n being 50, right? It's 2 to the 50. It's a big, huge number. And do you think we in practice we talk about 50 variables? Do you think that's practical to have 50 variables? You bet. 50 variables is actually is not really that many. So the worst case, when I say worst case, I'm talking about the simplex goes over all possible dictionaries. And we see that there are too many. If you go through all possible dictionaries, that means how many dictionaries here are you going through? How many pivoting operations are you applying? Well, exponential. Exponential in n, number of decision variables, right? Am I making sense? Remember I said complexity means the number of pivoting operations as a function of the size of the problem. Size is n, right? Size is the number of decision variables. So as a function of n, the number of pivoting operations could be 2 to the n, which is bad. Okay. The good news, though, is that in practice, on average, simplex, the complexity is polynomial. And this is exactly why this is exactly why simplex method has been widely used in the industry, in engineering, and many other places because this is on average. It seems like it works out really nicely. Okay, even though the worst case scenario is bad, but on average it really works good. In fact, there are other methods for solving linear programming problems besides simplex, and there is a method which is proven that its complexity is polynomial always. Okay, the worst case complexity, there is a method which is polynomial time. However, no one uses it. Why? Because you cannot really implement it. Okay. So it's a theoretical, algorithm, but you can't really implement it using the computers. Okay, am I making sense? So just because you have an algorithm doesn't mean you can translate it into a machine. Engineers should know it better, right? You cannot. You have limitations of the machine, right? And you cannot, just because you have a construction, mathematical construction, doesn't mean you can implement it via a computer. So that's why people would use simplex, okay? Because on average it works out really, really nicely. Okay, so I want to end by giving you. I want to give you the worst case complexity I claimed. That is is exponential because the number of dictionaries involved could be exponential in n. And I want to give you at least one example where that happens. We're not going to go over that, but this is called Klee-Minty cubes. Klee-Minty cubes. The reason is, if you draw, I gave you the example for the n-dimensional case. If you draw the feasible region in the 3 dimensions, you'll see that the feasible region looks like a cube, but it's like a distorted cube. Did I make sense? It's like a distorted cube. And so the problem is maximize z equals to 10 to the n minus 1 x1, 10 to the n minus 2 x2 plus da 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 x1. So the power on 10 is decreasing. Okay? And then the constraints are, the first constraint is just x1 less than 1. The second one, notice that I have 2 times 10 x1 plus x2. And then the next one is 2 times 10 squared x1 plus 2 times 10 x2 plus x3. Notice that this is the row 3, right? This is row 3. Row 3, and then the fourth row, I have 2 10 cubed x1, 2 10 squared x2 plus 2 10 x3 plus x4 less than 100 cubed, and dot dot dot. At some point, I should This is the ith row. This row. This row here is the ith row, and I should put more dot dot because how many rows am I going to get? Nth row, right? Until I get to xn. And then the ith row will be, you can see the pattern, right? You can see the pattern, what's happening. And I just wrote down a formula for that pattern in terms of the summation. It's not a big deal for you. I just wanted to show you that this example that I have, it turns out that if you use the largest coefficient rule for picking, entering variables, if you use that, it turns out that the number of pivoting operations that's going to be required and to get to the final dictionary is 2 to the power n minus 1, which is exponential. Am I making sense? So that convinces you that the worst case complexity of simplex is exponential in the problem size. Am I making sense? Now, this type of complexity issues might not have been discussed in an introductory programming class, but if you take some courses in algorithms and stuff like that, then they will talk about complexities. In any case, why am I giving you this information? Well, just for the completeness purpose, that you should be aware of these things. We are not going to delve into this subject, but everybody, I think, should know a little bit about this. And just to be aware that there are these things, that complexity issues and the stalling issues with the simplex, and everybody should be aware of that. Okay, but we're not going to do a whole lot with those. So next time I'm going to speak about the geometry of the dictionaries, right? Okay, and we'll see geometrically what the dictionary represents. Is that okay? All right. I think I'm going to end today right here.